Aneh ya. Kura-kura sih.
Serius ora?
Si. Baru laptop.
Kok HP apa?
Baru tab.
Take me home. Ayo ngising nang telepon tutupi gedung pring dan garing
Belum masuk itu.
wis. Fotoku keren banget ya.
Anjing cilik kan.
Taruh kamu ini. Jangan orang apa PTN apa?
Orang. Berdua. Lebih dong.
Cilik cok. Kok kurang jelas ya?
Main full screen cuy ya.
Di in.
Oke.
Wis, siap.
Ya, ready.
Good night. Hey,
Evening.
work ready. So in this session, I will try to explain introduction to statistical learning and how we will explain why we need to model the relation between input and output, which we will call it F. And to try to know the difference between parametric and parametric models to model the F, and last we'll try to learn about difference between supervised and unsupervised learning, more on the mathematical term. So let's start with statistical. So let's say we are hired advertising consultant. Right? So the company that hired us using 3 different media: TV, radio, newspaper. So we know that company can direct this advertisement cannot improve the sales directly or even indirectly. We cannot ensure that they can improve the sales, but we can control the money that we spend on the advertisement. So we can rest assured that the thing that we invest on certain media is the most efficient investment. So what if we have data that, okay, so we increase a TV investment on advertisement, and then we try to observe the sales on steadily. So if we invest $10 on an advertisement, and how the sales behave, how do the sales behave, and then if we invest radio on radio, how and what's different between TV and radio when we invest on these two, right? Okay, so that's the kind of thing, right? Then we have input variables. Input variable, which usually we call input variables x, and then we have output variable or the observe variables. So input variables usually we call it as predictors or independent variables, or in machine learning features maybe we often call them features. And then the cells, or in this case, is output variables, the thing that we observe. Okay, it's called dependent variable because we assume that the cells, once again, we assume that the cells is depend on the input, on the independent variable. Right. In this book, the book often called it as a response. Okay, that's why, by the way. So the output is y. Right. So is the data set maybe. So in this case, we might find this is certainly a linear approach, right? This maybe a linear regression that, of course, then we know from this plot that TV is basically the most effective, and radio is second most effective, and newspaper, I don't know. I think newspaper is somewhat like it's not really effect with the cells. Okay, that's basically. So we've talked about the concept of statistical learning. How do where F is actually landed in statistical learning, and now we will try to
Astaga.
not only one, but two-dimensional data X. But in the real world, we might find a higher dimension. For example, we have p features, right? P features x1 until xp, but there's only one y, right? So we can write the formula, mathematical formulas like this: y is equal to fx plus what do you call error term? Okay, error term, random error term. Okay, so the thing that we need to take note is that error term, if we take an average of error term, they will have zero mean, zero. So it's because the error is we assume that the error is sometimes it's plus, sometimes it's minus. So if we take an average of it, it will become zero. So that's basically that's this y is equal to fx plus error term. And I think so. In this case, from this, we talk about how if we have more than one feature. In example, we want to model income versus years of education, and then we try to add another feature, a seniority. Right? So it's become two-dimensional. Okay, yeah, this is only, that's why the error term is zero, right? Like here, because there's a minus, there's a plus, and theoretically it would come zero. Okay. Now we after we talk about what is it introduction to statistical learning, and we figure out the F, what is F, and what is the error term. We'll talk about why do we estimate F. Okay, so there is two cases in in data science. I don't know how to put it. In this book, we call it uh, why do we estimate F? Because we want to know the prediction and the inference. So it is a really simple. It's a simple definition. So the prediction is where we only want to know the result. We don't so we only need the result. Like us, we only need the result is positive, neutral, negative. But in recent case, we need to learn the interpretability of the model. But in most cases, in NER, for example, we don't ask why Joko is a person. Like, of course, Joko is a person, but we don't need explanation of the model. Like, so NER is a prediction, but the sentiment emotion in our case is maybe is inference, because we want more explanation. We want more explanation of a prediction. So it's basically a prediction is when we only need the result, and inference is when we need the result and also the explanation of it. So okay, so let's see. Okay, China, we talk about it. We just talk about it. The error term, if we average it, it becomes U. So the average of uh, the y hat is it's the y hat is actually the predicted y. Okay, so because the error term is 0, we cannot get rid of it. Okay, so it's an estimate value. In prediction, F often treated as a black box, right? Because we don't need the inside the black box. We don't need to know what is inside the black box. So we kind of treat it like, well, F is F. I don't care what inside F. That's the prediction is basically okay. Okay. Oh, okay. Right. Uh, we'll talk about the here the accuracy of E of Y, and we will talk about the reducible error and the irreducible error. So in Indonesian word is error yang nggak bisa dikurangi dan error yang bisa dikurangi. The reducible error is basically well, it's the Y minus Y hat or estimated Y. It's the reducible error. We can reduce the error, right? We can reduce the error. Wait, okay. Oh, so someone. I didn't get the comment. Okay. So the reducible error is the Y minus Y hat or the predicted Y. Right. That's the reducible error. And the irreducible error is actually the error term, like here, right here. Why it's irreducible? Because in black box we never know. Sometimes because we assume, right? We assume that X has direct or indirect relation with the Y, but maybe we never know. For example, like for the 6 months they use blood donation, blood sample. Okay, so we want to know if someone has a risk of TBC from a blood sample. Maybe we can acquire SpO2 or the red cells or the white cells and so on and so forth. We can acquire that, but we never. But how if the 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 Y is actually relate to the patient's feeling on the day of the sample sample di hari di mana sampel diambil. How we never know such case, right? We never able to to gather all the features related to y because of what? Because we never know. Sometimes we never know how if the TBC actually related uh, to the length of happiness. How something like this. Some things that we never able to gather the features, or we it's too expensive to get features. Like, for example, maybe we want to model the sentiment. Oh, then don't say. We want to model the price prediction, right? But maybe we can acquire we we have the data, but maybe the data of the higher price, okay, we don't have data because it's too pricey. It's expensive. We can afford the data, right? So something like that. We never able to gather all the information that we need to model the y to x, right? Okay, so that's the irreducible level. Yeah, some things that, well, we don't know for sure, but we know that we never able to fit perfectly into the real world. That's exactly the error term, the irreducible error term. But we can reduce the predicted minus the actual number, right? The y minus y hat or y the predicted y, we can reduce that. So that's basically it of prediction. So yeah, accurate. The expected value of y minus y hat squared is this is y, right? And this section is y, and then this section is y hat. And I don't know why this came like this, but you know, so the the error is basically reducible error plus irreducible error, which simple by variance of the error term. Yeah, that's basically prediction. Okay, we don't care about we don't care about the explanation. We don't care about the inside of the model. So it rises the reducible error that and irreducible error. And then come inference. So inference is basically when we need we need the explanation. So TV investment actually increase the sales, right? Why? How much the increase? So that's the first question we want to answer, right? How? Why is increase and how much? And how fluctuate? How a lot of things come to our minds, right? Okay, so for example, this which predictors are associated with the response. So we have a lot of features, right? A lot of predictors, a lot of x1 until xp, right? So which predictors are directly associated with the response? Okay, we need to know, right? And then the relationship between each predictor and the response is what we need to know. So maybe the SpO2 and the red cells concentration of the blood is having a high relation with the uh, with the TBC to diagnose TBC people, right? So how is high red cells is actually related to TBC, or small amount of red cells is actually related to TBC? We need to know what is the relationship. Is it linear, or positive linear, or negative linear, or it's quadratic linear? We want to know, right? We want to know the relationship. Okay. Uh, can the relationship between y and its predictor be adequately summarized using a linear regression, or is the relationship more complicated? So is the y is actually linearly? We can assume the predictor and the y is linear, or is it more complex? Is it like we need it's a logarithmic function or something? We always ask that question. So that's inference. We need to in inference it's we need to know the side answer. So okay, so we got this number. The price prediction will so our model predict the price will be $20. The price of cars in the 2030 is gonna be $20. Why? Why then? Okay, what is our feature? Our feature is, for example, the fuel price. So the fuel price is high. Then the fuel price is higher each year. So why do the car price is getting lower each year? How it's possible? We need to know, right? Something like that. So that's inference. Okay, yeah. Okay, that is basically the inference. So the prediction is when you treat F as black box, so it rises. It makes there's something called reducible error and the irreducible error, because we never know the explanation of the irreducible error, right? But in the inference, it's manually explained. Okay, so we know why do we estimate F? Because we want to know the prediction and we want to know the inference. And how do we estimate F? Okay, there's a lot of things, but in this step we only learn about the parametric methods and the non-parametric methods. So the parametric methods is basically when you make assume of data and the y. So so when we try to model the x and y, we assume that x must be linearly related to y, right? Whether it's positive linear or negative linear, we don't care, but it must be linear. Okay? It must be linear. That's parametric method. So before we try to calculate, we make an assumption of the model. So it is a very high bias. Okay, it's not flexible because we need to have an assumption, but uh, it really fast. Okay, yeah. It's really simple. So we make an assumption for parametric methods have two-step model-based approach. First, okay, we make an assumption of the x and y linear. We assume that the x and y is linearly related, right? Okay, and then the second step, we actually calculate the coefficients. In this thing, we use this like we use this like this. So beta b1. So instead of so for example we have 20 features first and we have 200 data. Instead of we are going to 20 times 200 data, we go only 20 data. So we only need the p we only need a certain number of amount of parameters instead of we going right. So this is x1 at the row 1 and this is x1 at row 2. How this linearly how this related and how this affect the response? It's complicated. In parametric methods, it's not so complicated because we make assumption it's linear and we reduce the parameters to the number of the dimensions, right? Okay. So what we have a lot of methods to calculate the beta here. One of the most popular method is ordinary least squares. Okay. I think I have. Okay, so this actually right. Beta is calculated like here in ordinary least squares. X transpose times x inverse times x transpose times y, actual y. That's why. That's the beta. And the beta matrix is like this. Okay. So okay. Yeah, we can calculate it. Okay. Okay, that's parametric method. Right. So we know that parametric methods is fast, is easy, it's we can we can get explanation from parametric methods easily because we assume that every features has some kind of linear relation with response, something like that. So it's really easy to get an inference from parametric methods. Thing is because we make a huge assumption, right? We assume that the model has linear relation with the response or the y. It makes the model have a high bias. So the model's never able to some kind of fit the data perfectly. It never achieve overfit, but it in most cases they are underfit. Right. That's why that's why parametric methods rarely used in our case. Like, but the thing is, in more complex model, more complex, they have a lot of parameters. But the thing, when we have a lot of parameters, the problem rises. Maybe we can fit the data perfectly, but maybe we fit the data too perfectly, and when we try to different data, we get lost. Right? Performance is not so good. That's overfitting. Okay, so that's parametric function. We are very not flexible. We are very rigid. Parametric is very rigid form of statistical learning methods because it assumes that X has linear assumption, linear relation with Y. Okay, that's okay. Oh, so it is uh, example of if we have two features and we observe the income, so it becomes like this. So it's it's beta related to each features. So beta one here actually symbols the relationship features, relationship between education and income, and B2 beta two is symbols the relationship between the seniority and income, something like that. So it if we even if we have 1,000 uh, dimension of data, we only have it's very simple. If we use a neural network, 1,000, basically a million parameters, something, this is too much. But in parametric methods, it's really simple. But that's the problem is we never get to fit the data perfectly. Okay. Okay. So and then the non-parametric methods. Okay. So it's really the exact opposite of parametric. So when the parametric function make assumption about the correlation between X and Y, the non-parametric methods they don't make explicit assumption. So they try to learn the the relation by themselves. Yeah, uh, that's actually the big line in non-parametric models. Okay, so we don't assume the X have some kind of relation with Y. In opposite, we try to learn the relation, but in non-parametric methods, there's a certain level of assumption. For example, let's see, in tree, in decision tree, or yeah, in decision tree, for example, we kind of uh, make an assumption, right? In if the data has like a tree, so if this is bigger than 2 and or this is bigger than -1, so something like that. It creates assumption that the model actually uh, affected by the some kind of decisions, right? But it less decision tree is less region in linear regression for or ordinary least squares regression. But it's on the non-parametric approach. Okay. Okay. So okay, we know parametric functions make assumption about the x and y relation, and the non-parametric function don't make assumption about the x and y. So what is the trade-off? Of course, the trade-off between if we use non-parametric function, we're gonna have a good accuracy, a good number. We can have a less loss or bigger accuracy than the parametric function because it's more flexible. It fits data more flexible than the parametric function. Okay, but what is the trade-off? The trade-off is usually model. It's the more complex. The more complex, interpretable. Like we try to model with y regression. We exactly know if x1 is getting higher, the y is tend to get lower, and for the opposite, if x2 is getting higher, it's easy to get assumption like that in parametric function, flexible method. But in non-parametric function, maybe we can use fourth factor machine, right? Okay, so how do we know about that? Because SVM is actually so complicated. We can understand the inside of the model, right? So we like in ordinary squares we have beta zero, okay, beta zero or beta one. It really okay. So the beta one is actually plus, so we can know that x1 is actually uh, positive linear to the y, and beta 2 is negative, so we can know that x2 is negative linear to y. But in SVM, how do we know about that? We may able to get the inference of SVM, but it's really complex. You need to be master degree of something to get that from SVM. So right here's the okay. The less flexible the model is actually the high interpretability, and the higher interpretability, the higher flexible the model, we get less interpretability. So because it's more complex, it's not understandable by humans, or it it it's doing too much calculation, too much computation. So human is impossible to get the inference from that. So that it's basically the trade-off between parametric models and non-parametric models. Parametric models tend to have lower prediction accuracy, but they have higher interpretability. But the non-parametric functions, such as support vector machines, they tend to have a higher prediction accuracy, but lower interpretability because it's more complex. Okay, let's calculate. It sums all the things that we need to know. Okay. Okay, then supervised versus unsupervised learning. It's basically, I mean, you know this, right? Supervised is basically we try to we know the why already, but in unsupervised we don't know the why yet. Right? Okay. So in this book, they define some interesting uh, case. In our case, we always have complete data, right? And from x0 till xn, we have y0 until yn, right? But what if we only have if we have y0 until yn, but we only have x0 until xm, where m is less than n. For example, if you have 100 data, but we only able to get 90 input data. So how do we know about the rest of the uh, of the of the data, right? So there's come clustering, something like that. That's the case. Is actually called supervised and semi-supervised learning. When you fill some blank data, or yeah, something like that, with clustering, or not always doing something. For m observation, where m is less than n, we have both predicted measurement and response measurement. For the remaining n minus m measurement, we have predicted measurement, but okay, so we don't have the response, not the inputs. We never encounter something like this, right? So we really lucky. And regression versus classification problems is basically about the quantitative. Regression is quantitative problems, and classification is qualitative problem. Or in data science, or in our case, it's often called as categorical data. Okay. Yeah, this is basically it, and this is the next week material. So thank you guys. That's the end of my explanation.
Okay, thanks, Mr. Tito. Please give applause to Mr. Tito that convey the material. And then anyone can convey something to be discussion. Sivan? Okay, I have a question about parametric and non-parametric model. How about deep learning? Does it belong to parametric or non-parametric?
Definitely non-parametric model.
Non-parametric.
Deep learning never, because deep learning never makes enough from the data.
And for SVM non-parametric. Oh. So just regression that belong to parametric.
Yeah, there's more selection method. It's like, if it is more than X, then it's belong to class. It's selection, right? It's parametric.
No other algorithm that belong to parametric.
OLS, ridge regression, lasso regression.
Mas Adi baru gabung.
If I want to ask, what's the key difference between the non-parametric and parametric models in terms of the distribution?
I'm sorry.
What is the key difference between the parametric and non-parametric models, but in terms of the distribution?
Distribution of
data.
Data. I'm sorry. Data of X or Y. Y of.
Right. I mean, like, I just want to. Is it true? I just want to clarify based on your presentation. Is non-parametric depend or not depend on the any distribution, because non-parametric does not make any assumptions, right? And research is central. I think I don't know.
So actually, okay, I will answer this, but it's calculated in my memory. So let's. So my answer is the non-parametric, of course, have lower variance, and the parametric function response has a higher variance.
Hmm.
So uh, okay, this okay. Uh, right. So uh, I'm actually uh, it's the opposite. So the low variance is the parametric function. So the parametric function predict less variation of response than the non-parametric function. So non-parametric function have high variance actually. So they respond differently between another set. They tend to respond. For example, for set one and set two, maybe set one is have this x distribution, and this set two have x x. Oh, it's like x, but it's different distribution. But in parametric function, and the distribution of the response is maybe it's close to the same, or it's something like that.
Uh, can you open the link that I sent? Gitu.
Oh,
Can you open the link that I sent in chat Google Meet?
oh, oh, wait, wait, wait,
Google
wait.
Meet.
Hey, no.
Yes. Parametric function. There is simple neural network. It's belong to parametric.
I guess in this case, it's actually so. The thing is, it's simple neural networks compared to more complex neural networks. It's of course the simple neural networks is more parametric than the deeper neural networks. It's just about the level.
So what the
But the
assumption?
thing,
What the assumption that we use neural network as parametric models?
in neural networks, we have called neural, for example, right?
Yeah.
So we never know, right, the inside the neural, but we can take a case. For example, we have two neurals versus we have 12 neurons, right? So the simple neural networks is the one which have two neurons, and the more complex neural network is which the one have 10 neurons. Right? So maybe in two neurons, the first neurons is taken assumption if the x and the y is positively linear, and the second neurals uh, make an assumption if the x and y is negative linear. So it's basically parametric if it's only two neurals, right? Because it's kind of linear regression. We can take it. So any deeper and deeper or more complex networks, we can never take a guess because it's too much neurons. This particular linear is negative linear, and this is quadratic linear. This is negative quadratic linear. Oh, there's no negative quadratic linear. By the way, something like that. It's it's basically on the level. But I would say that compared to both, I think naive bias is basically non-parametric because if you take a look at naive bias, naive bias is actually I forget. Naive bias is actually parametric because I forget about the word naive. Why naive bias has uh, naive words on it, but I think it's because they make an assumption about the data. Hmm. I think nah. That's why student bias is actually a
Independent.
parametric. So if x0 and x1 is actually they don't have any relation. Like student bias assume like that.
Oh, param parametric.
Uh, I want to ask Anit.
Me? You're a speaker.
Everyone is a speaker.
Yes, you can ask to me, but Mas Adib yang menjawabnya.
I'm just arrived at the meeting, so I have no idea what you're talking about. So I think both of you must have discussion about this.
Discuss about parametric and non-parametric models.
What about the exercise? Have you guys take a look at the exercise or
Yeah.
something?
Exercise.
Oh.
Oh.
Okay, let's solve this.
Let's discuss the exercise.
Conceptual exercise number 1, page 52. For each of parts A through D, where's A? Where's D? Oh. Indicate whether we would generally expect the performance of flexible forest learning method to be better or worse than inflexible method. Okay.
Maksudnya apa ya?
What is the question?
In bahasa you indicate whether generally expect the performance of flexible statistical learning method to be better or worse than.
Okay. So this actually asks. Okay. So for each part through, so we have this case, right? A until D, right? So we will ask if we use parametric function or more flexible method versus inflexible method. Inflexible means parametric, flexible means non-parametric. Which one will have a better result and why?
Oh, okay. Flexible parametric.
So first case.
Seperti flexible non parametric ya?
Yeah, flexible non-parametric.
Samples.
The sample size n is extremely large and number of predictors p is small. I'll say parametric function will do better.
Give us the reason, not the answer.
Okay. Okay. So so I think uh I think because uh, they make less assumptions on. I think usually small features is a simpler data set. Usually, of course, it's simpler than higher data set, right? Because they have only they have smaller features. Uh, and and in parametric function, if we have higher dimension, we tend to make a lot of assumptions. So in features one, we make one assumption. Features two, we make one assumption. It's a lot of assumption on the base, right? But in non but when we have a smaller number of keys, number of features, we uh, we only make we make smaller assumption. Therefore, we make a better prediction than when we have a higher dimension. Yeah, it is because data is less nice. But do we have an answer here?
I don't know. Is there the key of answer?
In the book, no, but I
yeah.
think they do have one in their website, but only for some numbers.
Ah, so we don't have it. No. Okay, so I think how about Asadip?
When the sample size is large, and which is, I think, in terms of training data,
Ah,
we do have a lot of training data, which is quite good to other non-parametric functions, especially if you are using kind of neural network, deep neural networks. So I'm not really sure about if I think, yeah, I can see your point that we do have small number of feature that it might be more simpler, right? More simpler to learn, maybe less.
Assumption.
Yeah, maybe we don't have any assumption about the data yet, and we can use. I think if we are using more flexible method in case of the data is extremely large, even though the number of predictors is small, I think, in my opinion, it will perform better compared to if you use inflexible method, even though the number of variable is small relatively. Yeah, but to be honest, I do not know the correct answer. I think we have to check the answer if they do have in their website. I'm not really sure.
okay. Well, I think I'm agree with Mas Adip. So, I do when we have larger n, larger samples, it's rarely if all the n or all the rows of the data is linear. Non-parametric will do better.
And I think one thing that I want to note is that sometimes in terms of non-parametric, in the class of non-parametric models, we could also rank them in terms of their flexibility. So in this case, flexible versus inflexible doesn't always, like, flexible always non-parametric, inflexible always parametric. Sometimes even in class of non-parametric, we can rank, okay, this method is might be less flexible compared to this particular method, so on and so forth. So for example, if you use 2 layers of deep learning, which is 2 layers of neural network, which is non-parametric, and you compare that to 1,000 layers of deep learning, both of them are non-parametric, right? But we can safely assume that the more depth you have in your layers, the more flexibility you have compared to if you only have 2 layers. So it's not always the case that flexible is flexible and inflexible related to parametric non-parametric. So yeah, I think the term of flexible is inflexible might be related, but it's not always the case.
Yeah, and the answer is actually the more flexible method.
Okay.
Yeah.
Okay.
Okay.
So
Okay. Part B. No one saw the part written.
Do not see the answer yet.
so the answer is
You already have someone
No,
already
the answer
non-parametric.
is yeah, non-parametric will do better.
flexible.
Yeah, flexible, more flexible method.
We are talking about flexible versus inflexible.
You say
Inflexible,
uh,
not
Tito say
param-
that flexible is non-parametric and
Yeah, in general, yes. But in this question, we are talking about flexible versus inflexible. And even like I said earlier, that in terms of non-parametric, the method of all non-parametric, we still have like kind of rank between okay, this method is might be less flexible compared to the other method. Even both of those methods falls under non-parametric. Okay,
Okay.
can you understand me?
Yeah, I think I can understand, Mas Adib.
How about Hanif? Because the one who
I'm
asked is
still
Hanif.
confused.
Okay.
In bahasa maybe you can in bahasa.
Oke. Gak semuanya yang non parametrik. Maksudnya, ya non parametrik tuh kalau secara general memang tidak fleksibel. Lebih fleksibel dibandingkan yang
Iya.
parametrik. Tapi di dalam kelas non parametrik pun kita masih bisa meranking mana yang lebih fleksibel, mana yang enggak. Contohnya kalau misalnya kamu punya deep learning metode yang 2 layar, kan itu masuk non parametrik kan, fleksibel dia. Tapi kamu punya metode deep learning tapi 1.000 layar, sama-sama masuk dalam non parametrik, sama-sama masuk dalam fleksibel. Tapi kalau kita kebandingkan 2 metode itu, otomatis yang satu lebih fleksibel dibandingkan yang lain kan. Jadi fleksibel dan non fleksibel itu mungkin secara garis umum mungkin terasosiasi dengan dengan parameter non parametrik. Tapi karena kan berbicara tentang fleksibel dan fleksibel, mungkin kita nggak usah terlalu lihat pada parametrik non parametrik. Kita lihat apakah sesuatu yang lebih fleksibel, metodenya lebih bagus dibandingkan tidak fleksibel gitu. Karena bisa jadi dalam yang non parametrik pun ada yang fleksibel, ada yang kurang fleksibel, ada yang lebih fleksibel gitu.
Oke.
Nip, coba denger Nip. Dengar nggak?
Apa?
Suara AC.
Hah?
Suara AC.
Astagfirullah.
Tidak ada AC kan di kos Anda?
Saya tidak mudah panas.
Apartemen Pak Iqbal, Zoy. Ada AC, Zoy.
Wong Cilacap. Next.
Okay. B. The case of B. Number of predictor B is extremely large, and the number of observation n is small. Okay, this is it's tricky. If I encounter this case, maybe I will do some kind of features reduction and then use linear regression or logistic regression or another more inflexible method. But if we cannot make it the features reduced, I think I'll use the more flexible method.
More flexible. The number of P is extra large and the number. Apa? Oh ya, terima kasih.
How about
Satu aja.
nanti the other answer?
Dua juga boleh.
Oh, maaf.
Kebanyakan banget soalnya.
Terima kasih ya.
Sausnya nih.
Okay, excuse me. One.
Lagi.
Udah, nggak apa.
Ini lagi.
Udah mau ngasih.
What would the answer?
Sausnya.
Makasih ya.
What is predictor?
Predictor is the features.
Oh, dy.
The X.
X.
And the observation is the
Dy.
input. Oh, dy.
Okay. The predictors is the X, and the observance expression is Y.
The number of observation is the number of data.
Data kan?
Yeah.
The number of predictors is the number of features,
Yep.
right? And the number of observation,
Yeah,
which is
data.
the size of the data, which is I think quite the opposite of the first one. Where in the first one we have a lot of large data, but we only have small features. Whereas the case of B, we do have small data, but we do have a lot of features, right? So how about the one who answered the first questions should not answer.
Okay.
I think we should give the opportunity to other people to give his or her opinion. I think we don't have any girl in here, so yeah. So who want to give the opinion, his opinion of the B, the case of B?
Fajri.
Lo.
Kok milih-milih ya?
Aduh, dihapus.
Sifwan, what is your opinion?
Okay, let me try to
Browsing.
give my opinion.
Before that, I think we should give the speaker the authority to decide who will answer the next question, right? So yeah,
That's a good.
Tito, it's up
That's
to you.
good.
Oh,
That's a really good decision, actually.
just
Okay, Sifwan, what is your opinion on this case?
So I think when the predictors is extremely large and the number of observation is small, I want to use flexible learning method because I think like the question A, sorry, the predictor is small, but we use flexible method because they have extremely large n and they have big variance. I think, is it true? My logic.
Yeah.
Yeah.
That's good.
And when we have an extremely large predictor, it means the observation, the data, even it is small, they small, but they have a lot of variance too. So I think I will use a flexible learning method because they have big variance. Yeah,
Okay. Yeah.
that's my answer. I know it's, and I do not read the
Big answer key.
yeah, answer sheet.
You don't read?
No,
Okay.
I read the answer of A.
Okay.
You didn't read, but just take a pic, right?
Yeah. Is it true?
Okay. The moment of truth. Or anyone want to give an opinion before we open the key? Fajri, maybe. What is your opinion?
Same as Stephen.
Oh, Fajri is.
Same as Stephen gitu aja.
I think Fajri is AFK. Okay. The part B. Okay. Oh,
Wah,
Yes.
yeah,
worse,
but
worse.
Worse. It worse. Not
yeah,
just
but I think it's we wrong because I think the flex the inflexible method they with the with less data I think they perform better even though the number of p is higher uh, because uh, it so the inflexible method in OLS, okay, the ordinary squares. The rest I will talk in Indonesian because it's hard. Uh, jadi karena di OLS itu menggunakan koefisien beta 0, ini contoh aja, contoh yang infleksibel, beta 0 sampai beta p. Jadi kenapa parameter inflexible method lebih mudah daripada flexible method? Karena daripada kita nge-fit seluruh data, kita coba nge-fit number of dimensionnya aja. Oke. Jadi it's kind of ini jadi kayak apa ya ya emang ini tujuannya dari bukan tujuannya ya inilah kenapa karena ya inilah keunggulannya daripada fleksibel gitu. Tapi ya itu tadi mungkin kalau datanya lebih banyak ya fleksibel method menang lah.
But the point is when we have big data, we need better use flexible, and if we have lower or smaller data, better use inflexible.
Yes, and I think it's better to reduce the predictors. So we only use associated features only. So sometimes we have just features that don't relate to the y. It's better than. So we have some kind. In data science we often use like curse of high dimensionality, right? You never heard about it? We often heard that, of course. I think it's very often, right? The curse of high dimensionality. Yeah, because I think I don't know why high dimension sometimes it makes the model performance worse. Okay, so that's why we need to reduce dimension. So we only use the related features. Yeah, I think.
I want to comment on Sivan's statement earlier that if we have more data, we should use non-parametric, which is not necessarily true. Imagine that we do have 1,000 of data, and we know the underlying structure of. I'm sorry, you saying that using non-parametric or using inflexible method? Oh, non-parametric. Okay, so yeah, I think we should come back to the definition of the parametric versus non-parametric, right? So parametric method we tend to have like assumption about the distribution of the data. So even though we do have like a million of data, and if we already kind of know what kind of the distribution of data, for example, if we do have 1 million of data and we know that based on the plot or something, the data is kind of linear, we could use simpler linear regression or something. Like we do not need to use like 10 layers of deep learning or something like that. Even simple linear method, if the data is linear, will be more than enough. So yeah, I think it's not really about the size of data. I think it also depends on, yeah, again, it depends on whether we do have assumption of our data or not, whether we know the underlying journey, underlying uh, distribution of our data, something like that.
Oh,
So, but in case if we do not have that knowledge beforehand, I think, yeah, it's a more safe way or safer bet to use more less flexible methods such as neural networks. But if you know the relationship or know the distribution of the data, why you have to use deep learning if you can use simple linear regression or linear classifier, for example?
Oh, okay, okay.
all right. Next question, please.
Okay. So the next, okay, the relationship between the prediction and response is a uh, Pak
Pak D.
Pade,
Ada.
you there?
Aku nggak ngerti aku.
Simple ya. Relationship between.
Jelaskan tuh pertanyaan dalam bahasa Indonesia, siapa tahu mungkin bahasa Inggris nggak tahu, bahasa Indonesia tahu dia.
Respon tuh.
Oke. Uh, jadi hubungan antara data atau input dan output uh, sangat tidak linear, non linear. Sangat tidak non linear.
Karena ilmu saya ini lagi tumpul sekarang ini ada.
Apa di?
Okay. We didn't get the answer. Okay, Hanif, what do you think?
Me? I
Yes.
my feelings say that flexible is better than
Yeah.
inflexible
Very high.
because yes, yeah, highly nonlinear. Yeah, because highly nonlinear and we don't know what is the distribution.
Yep. Yeah. How about Sifat?
Me? Yeah, because
Yeah.
I have already knew about the distribution. Cheating. So I think I agree with.
Okay.
Yeah.
Yeah.
What's the answer in the cheat sheet?
The answer is actually you're right.
Yeah.
Less restrictive on the shape of it. What it mean? It's
Tidak mengekang.
restrictive apa ya?
Mengekang.
I think when you restrict, when you're more restrictive in linear regression, you make an assumption that every good response and the predictors are linear. So it in nonlinear method, of course, it just it's not make you better, right? Because in linear regression you make assumption. You're not flexible enough to learn about the data. Right. Yeah, I think I'm there.
Wait. Jadi apakah selalu kalau parametrik selalu linear?
Not always linear. I will say simpler.
Restrictive of the shape of the shape.
Anyone want to add?
I still don't get the point.
Jadi gini, kalau menurut saya, wah, jadi kalau misalnya kita tahu dia itu bentuk datanya kayak gimana, bentuk distribusinya kayak gimana, misal contohnya linear, berarti kita ini enggak, kita masih apa ya? Kita bilang datanya linear nih, gitu. Berarti kan kita punya asumsi ke data itu kan, ke distribusi data itu. Makanya dia lebih bagus pakai apa tadi, linear regresi mungkin. Nah, jadi kita pakainya yang in inflexible tadi, lebih ke inflexible. Jadi flexible is worse than inflexible. Kalau kita tahu distribusinya itu linear. Kalau misalnya kita nggak tahu distribusinya atau malah distribusinya non linear kayak tadi, alangkah baiknya kalau kita menggunakan flexible learning method, bukan begitu?
Oh, dah itu betul itu.
Betul ya?
Gak ada yang harus ditambahkan. Kecuali kalau Hanif masih bingung. Ada yang lain masih bingung gitu.
Okay, Hanif, are you alright?
Alright.
Okay. You're okay to moving on. Okay.
Yes. Next.
Okay, I think the next case is the most abstract case. Okay. The variance of the error terms, example, variance squared is equal to variance of error. Is extremely high. So if the error terms or the variance of error terms is high, what does that mean actually?
Pick one.
Okay.
Lah kok lagi, Pak?
Oh lagi. Pak Wicaksono, are you there? Oh, I think he's AFK. Pak Zibua, silakan Pak Zibua.
How about Mr. Tito? Are you there?
Okay. No, I'm the picker. Okay, I'll try to answer this. Friends of the error. I don't know what that means.
It mean ini ya, the yang tidak bisa diubah, error yang tidak bisa diubah.
Yeah, the irreducible error. Yeah. Okay. I would say if the variance of the error is high, okay, so the variance of the response is also high. Okay, that's my assumption. If the variance of the error is high, then the variance of the assumption of the predicted value or y hat is also high. Therefore, what the? I don't know. Okay, what is this? I think flexible method is gonna be the answer because when you have a when you have extremely high variance of the error, it means the error fluctuates. When the error fluctuates, we need to know where is the local maximum, local minimum, or the global minimum. So, I don't think they're. I don't know. Flexible method. If we use deep learning, we have some kind of gradient descent method to minimize the error, so we can rest assured because the optimization method. The optimization method will make sure that we will find the lowest at the lowest error. Well, we hope, but in reality, it's never the global minimum. It's always the local minimum. But but that's my answer. Okay, flexible method because uh, we need to know the, I don't know if it's case or something, but is anyone want to add the answer or want to maybe have different answer?
Yeah.
I think it's inflexible method.
Because
Just simpler reason.
Why?
Just
Why? We don't need the answer. We don't need the answer. We need the reason why.
that is a simple reason because A is flexible, B is inflexible, C is flexible, so D is inflexible again.
Oh, come on.
I will agree with Nico because
That is so not data scientist, dude.
That's
It's a rule based.
the data science of data science.
It's a rule based method.
No, that's gambling.
Okay, so Pak Zebu apparently want to give an opinion.
man, I just wanna
Agree with.
tell you that I agree with Tito more than Hanif because because I think when the error term variance is big,
Hi.
is extremely high, so I think the distribution of the data is uh, non-linear or is non complex, yeah,
Complex, yeah.
complex. So when we have complex data, maybe I think it's better to use flexible method than inflexible method.
I think so too. I think
Yeah.
so too. I agree with Zibu.
No, you.
Flexible method is better.
Okay, let's find the answer.
Wait.
Oh, okay.
Continue.
Oh, okay.
Well, the variance of the error term is extremely high, which means that I think I'm kind of agree with what Tito just said. The predictor might be have. I'm sorry, the response might be have a lot of high variance. So I think if we force using simpler method, and I think the error might be a lot bigger. So I think we should try to use much more flexible method because yeah, with I think it I don't know whether you already talk about bias versus variance, right? If we do have like lower higher variance and lower bias, which normally the case of non-parametric method, and we do have like method that higher high in bias and lower in variance, which is the case of normally
Non-parametric.
higher high bias in non-parametric, lower bias high variance in non-parametric. So I think in this case, I think the flexible method normally will perform better compared to inflexible method.
So let's see the
Yes.
answer.
You already see the answer. Oh, actually, it's worse.
Hey, okay.
It's more likely to overplay. It really doesn't explain the detailed answer. So why?
Flexible learning method will perform worse because it will be more likely to overfit.
Why?
I'm not really
Oh.
sure. How about
For
we go back to bias and variance?
I win. I win. Rule based is better.
You just gamble.
Rule based is better than data science.
Kind of forget which page.
34.
1, 2, 4.
It started from.
Okay. As the general rule, we use more flexible method, the variance will increase, right?
Yes.
Okay, and the bias will decrease.
Oh,
So maybe because
variance.
if we use flexible methods, since we already have high variance, the variance, the error variance will be increased even more, right? Maybe that's why we should use more inflexible.
Yeah. Uh, I, so I think it's the higher variance is the problem of the flexible method.
We cannot hear you, Tito. Maybe you are too far from the microphone or something.
Mati ya. Mati.
Oh, check.
Oh iya udah.
Okay.
Oh, so when I close the browser, the microphone close to. Okay. So I think higher variance is the problem with flexible method, right? Because the flexible method has high variance. Right? So to solve that problem, we need to use a lower variance method. It's inflexible method. Okay. Yeah. Something like that.
I still don't get the point.
Yeah. Words to I know
How
that.
how if we explain with visualize with
Oh,
scatter plot,
oh, oh. Yeah, yes.
scatter plot, or yeah, in diagram, yeah, or yeah,
Yeah,
scatter plot.
please.
Maybe Hanif will be better.
No, itu yang udah terlanjur. You can open.
Okay. I think I'm gonna get that. Sorry. Okay, wait. How do we plot with pain?
Ya, pain.
How about pain? Right?
Pain rasa sakit.
No.
Pain.
Pengen
Grita.
musuhnya Naruto.
Pain.
Grita is sorry. No problem. Please wait. I think the high variance of error leads to higher variance of response. So the higher variance of response leads to higher variance of data. So if we have a higher variance of data, then it will the data is it's not linear. No, it's not that linear. The data is say
More complex.
uh yeah, more complex. It's too complex.
Too
Okay.
complex.
It's too complex. Not only complex, but it's too complex because it stated that it was extremely high, right? So it's too complex. It's very complex. So when we have flexible method, they tend to overfit. So it's because it's too complex. So yeah,
Wait. In the question, it's error term in data test or data train.
I don't know. I think it doesn't matter. I think it's a data train.
Because if it's data train and if the model is
No,
overfit, so the variance I think is low.
is it?
Jadi kalau misalkan overfitting dan overfitting, harusnya data trainnya itu mempunyai variansi yang rendah kan, kecuali kalau memang variansi errornya itu tinggi di data test, mungkin itu memang overfitting.
Right. Yeah. Yes. But I understand that. But the thing is, how do you avoid the overfit? Not that question. I think. So I think it means in the earlier stage of learning, right? Because um, when the difference of error is higher, then I think it's like a chain of reaction. When the variance of error is higher, we have a higher variance of response. Because we have higher variance of response, it's probably we have a higher variance of data. Yeah, I think I don't know, man. But I kind of understand why the answer is this. I can understand.
Maybe can you open Paint online? That is simple.
Yeah, that's
Great.
okay. It's so slow. Okay.
Uh, let's visualize how model overfit. Jelek banget. Can
I use mode. Okay. For example, we have this guy.
high variance or distribution is too complex. Itu mah linear. Jadi linear.
Okay. Let's see if we have something
Okay.
to. What if like
It
this?
is
Right?
a response or
This is actual data. Actual data.
actually okay.
Right. Okay. So how about this?
I think it
Yeah.
complex.
It's very
Okay.
complex, right? It's high variance. So if you use flexible method, I think they will kind of, you know, tend to. Okay, let's do use.
McLean.
No. I will find the eraser. Let's erase. No. Let's
Z. Ya ampun.
so reasonable this. This. Okay. So actually, if we have an
Sorry, your voice is too slow. It's too slow. Yeah. Okay.
check, bro.
Yeah,
Can you
okay.
hear me? So actually, if you use a flexible method, I think
they gonna use this, right? Something like that. They kind of doing like this. I think. Yeah, I think it's if we use the uh, flexible
Oh,
method. But what we want to use is actually like this, right? If you guess, it is. I think it's kind of sinusoidal methods,
okay.
right? I think it's better. Yes. I think that's why flexible method.
Hmm.
I thought that
Perform
was
better.
linear method too. So you want to draw time series or a sine function? I thought that was straight line.
Uh, gimana Mas Adib?
I kira tuh kamu tadi rencana awalnya tuh
Iya.
straight line gitu. Oh ternyata tuh
Iya,
fungsi
tadinya kita kira mau yang straight.
gelombang. Ya, Mas.
So it's a flexible method line.
Yeah, I think that. Yeah.
Hmm.
It's the inflexible, right? Because they kind of reach it, so they don't make a huge turn on every data. But in flexible, they will overfit data. So this is if you use flexible, in my opinion, you will do something like this.
So we can say that if we have high variance of error, so the overfitting too high too. Yeah.
Yeah, when difference of error is incredibly huge.
Hmm.
Well, I think we can just to stop the you know some anticipation of overfitting. Right? We know the trick. Stopping, dropouts, something. Maybe we can use it. Okay, I think that's the last number. That's the last question because it's already 9:54. Yes, it's fair to sleep. Before I close, is there any question? No question? Okay. Just a reminder, next week will be presented by Fajri.
Fajri, are you there?
Okay, if you make in time, it's okay. We will discuss it together, or yeah, we will discuss it together, basically. So don't scare to present.
I think it's better if we do the exercise individually, and if you have any question or something, just raise it in the group.
Yes,
We do have a lot of questions, which is, I think, since the question is like fundamental questions, it's not like technical or something. So you should try to answer the questions, and if you have any problem, just ask the group. Maybe someone will answer it to you or give some explanation.
Okay.
Sama-sama bingung nanti.
Well, at least we do have the cheat sheet, right? So if we both confused, we can look at the correct answer and make some assumption about it. Okay, what's the topic for the next?
Next is about assessment of the model, about quality of it. It's pretty simple about MSE.
Assessing model accuracy.
It's about the loss.
Bias and variance maybe.
The accuracy.
So chapter 2, chapter 2, 2.2.
2.2.
Okay.
Page. Okay, if there's no question, thank you for your participation. Uh, I'm really glad it's really good sharing, and I hope we can see again. Like, thank you and good night.
Thank you. Good night.
Bye.
Have a good night.
Ya kabarnya Mas Adip. Loh, hilang wongnya. Aduh. Aku nggak dong.